What if I told you astronomers have discovered a black hole that appears to be breaking one of the most fundamental rules in astrophysics? A quasar named ID 830 seems to be growing at 13 times faster than the cosmic speed limit set by physics. And if that's true, it could rewrite our understanding of how the first supermassive black holes formed. The object at the center of this discovery is a distant quasar called ID 830. A quasar is the extremely bright core of a young galaxy powered by a feeding supermassive black hole. When matter spirals into the black hole, it heats up, glows intensely, and can outshine the entire galaxy around it. ID 830 existed more than 12 billion years ago, meaning we're seeing it as it was when the universe was still in its infancy, only about 1 billion years after the Big Bang. At that time, black holes shouldn't have had enough time to grow enormous, yet ID 830 is not just massive, it's growing at a rate that appears to defy the rules. To understand why this is shocking, we need to talk about something called the Eddington limit. The Eddington limit is the maximum rate at which a black hole can steadily grow. Here's how it works. When matter falls into a black hole, it forms an accretion disk. The gas becomes extremely hot and emits radiation, including X-rays. That radiation pushes outward. At some point, the outward radiation pressure balances the inward pull of gravity. That balance point is the Eddington limit. If a black hole tries to eat faster than that limit, the radiation it produces should blow away the incoming gas, essentially choking off its own food supply. It's like trying to pour water into a funnel faster than gravity allows. Eventually, it spills over. For decades, this limit has been considered one of the fundamental regulators of black hole growth, but ID 830 appears to be exceeding it, not slightly, not twice, but 13 times the expected limit. Astronomers used advanced instruments, including the Subaru telescope, to observe ID 830 in multiple wavelengths. They analyzed the brightness of the quasar, the motion of gas in the accretion disk X-ray emissions from the corona radio emissions from jets. By studying the spectral lines, the fingerprints of elements glowing near the black hole, researchers estimated its mass and calculated how fast it must be accreting matter to produce that brightness. The result? A growth rate equivalent to roughly 13 times the Eddington limit, a phenomenon known as super-Eddington accretion. But here's the twist. At such extreme feeding rates, models predict the structure of the disk should change dramatically. The radiation field should disrupt jet formation. Yet ID 830 is emitting both strong X-rays and powerful radio jets simultaneously. That combination is rare and unexpected. Normally, when black holes approach the Eddington limit, their accretion disks become unstable. Radiation pressure increases, jets may weaken or disappear. But ID 830 is growing extremely fast, emitting intense X-rays, producing a stable radio jet. This suggests one of several possibilities. 1. Temporary feeding frenzy. A massive cloud of gas may have suddenly fallen inward, creating a short-lived burst of extreme growth. 2. Thick accretion flows. In super-Eddington systems, gas may form a puffed-up disk that traps radiation, allowing matter to keep falling inward. 3. Geometry effects. Radiation may escape in specific directions, reducing outward pressure in others. 4. New physics. While unlikely, extreme environments sometimes reveal gaps in our theoretical models. Scientists are cautious. They're not claiming physics is broken, but they are saying our understanding may be incomplete. One of astronomy's biggest mysteries is this. How did supermassive black holes grow so large so quickly after the Big Bang? We've observed black holes with billions of solar masses less than 1 billion years after the universe began. According to standard growth rates limited by the Eddington limit, that timeline barely works. Unless Black holes sometimes grow much faster than we thought. If episodes like ID 830 are common in the early universe, that could solve the mystery. Instead of slow, steady growth, black holes may have experienced intense growth spurts, cosmic growth explosions, allowing them to reach enormous sizes rapidly. This discovery may be a missing piece in the puzzle of galaxy formation. Science demands skepticism. Possible alternatives include overestimating luminosity, underestimating black hole mass, temporary flaring events, beaming effects, exaggerating brightness. Astronomers are planning follow-up observations in X-ray, radio, and optical wavelengths to verify the findings. Future telescopes may detect more objects like ID 830. If they do, and if they show similar behavior, this won't just be a curiosity. It will become a new category of cosmic object. It's important to clarify. This does not necessarily mean Einstein was wrong. General relativity still governs gravity extremely well. But extreme astrophysical systems often reveal complexities in how matter behaves under intense conditions. The Eddington limit is based on simplified assumptions: spherical symmetry, steady inflow. Real black holes are messy, they're chaotic, they're turbulent, and sometimes they surprise us. So what do you think? Is ID 830 a rare cosmic fluke, or evidence that the early universe was far more violent and dynamic than we imagined? If you enjoyed this deep dive into super-Eddington black holes and early universe quasars, hit like, subscribe, and let me know in the comments if you'd like a full breakdown of how accretion disks really work. Because the universe still has secrets, and we're just beginning to uncover them.